Hi, this is physicsfarm.com, and this lesson is on graphs of motion. Graphs of physical motion are often shown one on top of each other. The reason that that's done is because there's a common time axis. So in this case, we can see that these three graphs all have the same axis with the same units, in this case, time in seconds. You can see that the labels for the y-axis, however, are different. We can see that the top one is position in meters, the middle one is velocity, which is a vector in meters per second, and also the bottom one is a vector acceleration in meters per second per second. That's how it's commonly presented, and you'll also often see these kind of dashed or vertical lines on the time axis to show the similarities or these common events that occur between the three different axes. Okay, let's take a look at an application. Let's start with the number line and our three axes of position, velocity, and acceleration. And let's go ahead and label the x-axis with time. And we'll also do the y-axis. The y-axis is in meters for the top graph, meters per second, and meters per second for acceleration. In order to build the physical model, we'll define our number line and we'll label it in x position of meters. And I've put a little car on the number line at time equals 0. And let's go ahead and plot some of these positions. We'll say that at time equals 1 second, it's 3 meters away. At 2 seconds and 3 seconds, it's 6 meters away. 4 seconds, 12. 5 seconds, 18. And then just for fun, at the end, we'll say that it goes back. I've drawn it upside down so we're not seeing cars on top of other cars, but it's on the same number line. So at 8 seconds, it's back at 9 meters away from where it started from, and at 10 seconds, it's back to the origin or where it started from. Okay, so let's go ahead and label our position graph as well as draw in those common time points. So you can see I've labeled with vertical lines time 1 through 10. And let's go ahead and start plotting the position on our position graph. We know that at time 0, it starts at 0 meters away, so we can go ahead and plot that. And we also know that at 1 second, it's 3 meters away, and at 2 seconds, it's 6 meters away. I've drawn that, and in this case, we're going to use the assumption that the car is moving at a constant velocity and that it's not accelerated. So its velocity is the same between 0 and 3 seconds. Therefore, I can connect these points with a straight line. We'll also see then that between time 2 and 3 seconds, the car remains at 6 meters, and therefore we can see now that that position graph becomes a horizontal line. If we kind of continue in this process, we'll see that at times 4 and 5 seconds, we can go ahead and plot those positions of 12 and 18 meters respectively and connect those with a straight line. Here's where it gets a little interesting. We can take a look at the slope of that line, and by definition from your math class, you'll remember that the slope of a line segment is the rise over the run in slope-intercept form. It's often given with the variable m. In physics class, we can say, all right, let's go ahead and let's adapt this from our math class. We know that the rise over the run is also the change in y over the change in x. But in this case, the change in y, as it turns out, although it's a little bit confusing, is the change in x position. And the change in x is the change in the time interval. So we have delta x over delta t. This is important because the change in position, in this case horizontal position, over the change in time in physics is defined as velocity. Okay, let's go ahead and find our velocity by finding the slope of that line segment from 0 to 2 seconds. We know that it's y2 minus y1 over x2 minus x1. And if I go ahead and plot those points in, y2 minus y1 would be 6 minus 0, and x2 minus x1 would be 2 minus 0, which is going to give me 6 meters over 2 seconds, or I can say that the velocity during that time interval from 0 to 2 is 3 meters per second. I can now go ahead and plot that on my velocity axis, which is the one in the middle, and I'll see here that I get a horizontal line, that the velocity at all points along that segment. Doesn't matter whether it's at 1 second or 2 seconds or 1.5 seconds or some arbitrary time between 0 and 2 seconds, it's still moving at 3 meters per second. Using the same velocity calculation, by finding the slope of the position versus time graph, I'll see that that horizontal line from 2 to 3 seconds will yield a velocity of 0. It's not moving. That makes sense. Okay, so the velocity from time 3 to 5 seconds will be the next thing that we look at. We can find that by finding the slope of the position versus time line segment from 3 to 5 seconds. I'm using slightly different notation in this case. Instead of 2 minus 1, I'm using final minus initial. So I'm simply saying y final minus y initial for that time interval over x final minus x initial. That's going to yield 18 minus 6 meters, since my final y position is 18, my initial is 6, and in the denominator, my final x value, which is my time value, is 5 minus 3, will give me 12 over 6, 12 meters over 6 seconds, or 6 meters per second. At this point, I can go ahead and plot it on my velocity versus time graph. It's a constant 6 meters per second from 3 to 5 seconds. Notice that I'm going to be conveniently ignoring the jump exactly at 3 seconds, and we can talk about that in class. Let's go ahead and take a look at the slope of the velocity versus time graph. Again, we'll use the same mathematical formula, the change in y over the change in x, which in this particular case, adapted to these physics problems, is the change in velocity over the time interval, and that is also important. The slope of the velocity versus time graph, by definition, is acceleration. It describes the rate of change of your velocity. So we can go ahead and calculate that, although you probably will recognize that the slope of a horizontal line is 0. In this case, if I do it formally, I get the change in y over the change in x. In this case, my change in y is 0, 3 minus 3, and my change in x is 2 seconds for that particular time interval. I'm doing 0 to 2 seconds. And there I'll get that my acceleration during that interval from 0 to 2 seconds is 0 meters per second, or 0 meters per second squared. I've gone ahead and graphed that already on the acceleration versus time graph. So the slope of the velocity versus time graph is acceleration. The graph of the position versus time graph is velocity. Let's go ahead and move on. And I've gone ahead and graphed the acceleration from 2 to 3 seconds, and from 3 to 5 seconds, the slope of that horizontal line on the velocity graph is 0. So I've gone ahead and graphed the 3 different plots, position, velocity, and acceleration for time 0 to 5 seconds. From this point, why don't you take a minute and pause this video and see if you can figure out what the 3 graphs are going to look like from 5 to 10 seconds. Okay, so I've plotted in blue on the position versus time graph the car's position at 8 seconds, which we know to be 9 meters, and the car's position at 10 seconds, which we know back to be at 0, or back at the origin. I've gone ahead and connected those with a line. You should notice that the line now pitches downward, which means that the slope should yield a negative value. Let me go ahead and calculate that formally. We get y2 minus y1, which in this case, the final y position is 0, the initial y position is 18, and we can see that the denominator will yield 5. So I get a velocity from 5 to 10 seconds is negative 18 meters over 5 seconds, or negative 3.6 meters per second. That's the velocity, and it's negative because it's going back in the other direction now. That negative sign is showing the vector nature of velocity. I've gone ahead and plotted it now on the velocity versus time graph, and again we can see that the slope of the velocity graph, which is acceleration, is 0. So now we have a complete graph that represents the motion of this car moving at different constant velocities throughout its motion. The last thing I'm going to do is ask you to take a quick look at the area of the shaded region on the velocity versus time graph. If you remember your formulas for area, you'll see that the area is the length times the width, since that is a rectangle. And that in this particular case, when we adapt this formula to physics, we'll see that the length of that rectangle is velocity, and the width of that rectangle is time. You should remember then that velocity is equal to the change in position over the time interval, and therefore velocity times time is equal to your change in position. This is important. So the area under the velocity versus time graph will reveal what the change in position of the object is over the interval. If we do this numerically, we'll see that the velocity is 3 meters. That's the width of the triangle. And the length or the height of the triangle, if you will, and the width is the time interval times 2 seconds. 3 times 2, of course, is 6. Our units are meters, and that tells us what our change in position or our displacement is during that first interval, 0 to 2 seconds, which is consistent with what the illustration at the top of this page shows you. So we can see that we actually did move 6 meters during that time interval. We started at 0. We moved positive 6 meters and ended at a position of 6 meters away.